All right. Probably get a new marker out and see this is. We'll give it a shot. All right. All right. Can someone tell me how to do this? Emily, what do you think? Periodic table. Yeah, periodic table. Yep.
And then you read the oxidation states in the top right corner.
Good. So what's K?
+1.
+1.
-3.
Well, let's do that one last. What's all?
-2.
-2. Good. So if we have 3 oxygens, what's the total charge oxygen is contributing to this compound? -6. So this is kind of how I do it here. If this is -6, then this is garbage. Hold on. I keep hanging on to all these. I feel bad throwing them out, but anyways, back to this. All right, so this is -6. This is +1. So all 3 of these total charges must add up to 0. And this is the part some students get confused with. It's not that, let me rephrase that. The oxidation numbers don't add up to 0. The total charge does. So whatever this number is here, if you add -2 plus that number plus 1, doesn't equal 0 because you have 3 oxygens. So -6 plus a certain number plus 1, these 3 charges equal 0, and this is the total charge. These are the oxidation states. 2 different things. So fix it. It's not -3 because if it was -3, those wouldn't add up to 0.
+5.
Very good. +5, so that's +5, and that would be the answer. Now, sometimes this one, so good job, Emily. Sometimes this will have a subscript. All right, so I'm trying to think of an example. Why can't I think of an example right now? Like KCr2O4. No. Yeah. I'm losing it right now. Hold on. Maybe that's CR207? Yeah, CR207. All right. So KCr2O7. So whatever the total charge is on CR, so let's say it's a +6. Because there's 2 CRs, each CR is +3. So I'm going kind of quick with that, but this is easy because there's only 1 atom. So if the total charge is +5, the oxidation number is +5. Same thing here. But because there's a 2 here, if this is +6, that would be +3. Same thing as with the oxygen. Since it's -6, there's 3 of them, each one is -2. So just keep that in mind. On your homework, technically it would be K2. But that doesn't affect what I was saying. On your homework right here, number 4, A, B, C, D, and E, this is what you're doing. You're labeling oxidation numbers. So why am I reviewing that with you? Because anytime an atom loses an electron or gains an electron, we're forming charges and we're changing charge, right? So we have to make sure we can understand how to label before anybody starts losing or gaining electrons. So questions on that? All right, you guys are good with that? Okay. Okay, so now I'm going to explain this worksheet, which is also homework. It says on the top, balance, mass, and charge. I'll explain what that means. Find which species is oxidized and reduced. Find the number of electrons transferred. So I'm going to give you an example right now in your notes that looks just like this so that you understand how to do this worksheet. All right? Okay, so let's see, I don't want to give you the same ones here, so I'll give you something different. Let's go with, and your reference table should be out too. I know I told you to take them out. Go to table J, please, table J. Let's say we have K solid plus Fe plus 2. +1 AQ plus Fe solid. All right, copy that in your notes, then I'll tell you why we have table J out. So you have K solid plus Fe plus 2 yields K plus 1 plus Fe solid. So this is kind of an abbreviated way of writing a redox reaction. I'm going to write underneath it what the real reaction would look like. Don't copy it, just watch. because this is not normal where you just see an ion with aqueous. So all of these examples, when I say not normal, in real life, you can't just take Fe plus 2 and react with K solid. There's going to be something Fe plus 2 is bonded to, because ions don't just exist on their own. So this is example, this worksheet is similar to this example, and the Regents does this a lot. So I'm teaching you something you might see, but I'm also going to give you kind of the real way you would see it in real life. This doesn't really make sense to do it this way, but it's Regents questions. That's why I'm doing it. So in real life, what do I mean? You would take solid potassium metal. So I think I showed you that earlier this year. It's like a little gray piece of metal. So you take solid potassium and you dump it into a solution of iron nitrate, let's say. So it's FeNO3 2, and it's actually iron 2 nitrate, because Fe plus 2, iron 2 nitrate. So you would have a solution, so a beaker full of iron 2 nitrate. Okay, you stir it up, make sure it's all dissolved, and then you drop potassium in it. As a result, you would get KNO3 AQ and then solid iron. What type of reaction is this? Single replacement. Go to table J. Tell me why this reaction works. And the way the Regents will word it is explain why this reaction is spontaneous. Because K is more reactive than Fe. So Fe cannot stay bonded to NO3. What happens is K overpowers it because K is more reactive. K is more reactive, so it kicks Fe to the curb. Fe's by itself. Now K is with NO3. So I'm reviewing a few things at once here. Reaction types, table J. So K is more reactive than Fe. That's why this reaction works. And then we'd have to balance it, right? So we're not going to do that. I'm just explaining what they don't show you on top is what? What they take out. So what's in the bottom that isn't on top? Kaylin, you said it. NO3. The NO3 minus. NO3 minus is called a spectator ion. What do spectators do? Watch. They don't do anything. So NO3 doesn't actually partake in the reaction at all. They're called spectator ions. So on the Regents, sometimes they take those ions out because it's kind of pointless. There's nothing to do. The reaction has nothing to do with NO3. Why does it exist? Because you can't get Fe plus 2 in a store. You don't walk into, whatever, price shop and say, can I have Fe plus 2? And you don't get silver nitrate either, I suppose. But you can't order iron ions and they just deliver them to your chemistry lab. You have to get it in a compound. If I want iron ions, I need to put them or dissolve a compound in water so the ions are free to move around. Then I can react the ion. So it's kind of a long explanation as to what this is. So that's why this looks strange, K plus 1, AQ, and Fe plus 2. It's because they took out the spectator ions. So I like to explain the background so you have a little more understanding of what's going on here. So now we have to balance this. We have to balance mass, balance charge. So there's three things always conserved in a reaction. What are they? Conservation of mass, energy, and now charge is something you're going to learn. So you're always conserving mass, charge, and energy. The energy is not going to be shown. We're not going to talk about that. So we're just going to balance mass and charge. Then we're going to figure out who's oxidized, who's reduced. I'm going to show you those half reactions, and then we'll do another example. And then if we have time, we'll do another example. This is kind of the gist of this unit. It's just identifying reactions, balancing, and then doing the half reactions. So we're going to kind of learn everything today, and then just practice down the road. And then I'm going to teach you about two cells called a voltaic cell, which is a battery, how batteries work, and an electrolytic cell, which is something that we use for electrolysis or plating metal on things. I think I told you guys that I'm going to plate. I have these little keys that we can plate copper on, so we copper plate the key. It's kind of cool. So anyways, you need to understand this first before we can get into that. All right, so enough of me rambling. Let's balance this thing. So I'm going to use magnets to help us understand because I don't think I do a good job teaching this. I could do better. So let me try and do better with you guys. Let's say K is red, Fe is green. Okay. So from what you've learned already, does it look balanced? So forget what we're doing right now. Just kind of like erase your mind for a second. Go way back to when we first learned balancing. Does it look to be balanced? Yes. You have 1K, 1K, 1 Fe, 1 Fe. So mass is conserved. Dylan, wake up. What is not conserved? What is not conserved? Charge. So, Pat, what's the charge on K solid? Solid piece of potassium. Nope. Try again. Let's say this marker was made of pure potassium. I handed it to Morgan. Yeah, Morgan. Okay. She'd be okay. She wouldn't get shocked. She wouldn't be zapped. Why? Because it's neutral. All elements in compounds are neutral unless they're dissolved in water or they're in a compound, then it changes things. So these have charges because they're aqueous, but if they're solid, liquid, or gas, then they're neutral. So what's the charge? Zero. Same thing over here. Fe is 0. Okay, I'm going real slow on purpose because the first example is crucial. Okay, so mass is conserved, 1 and 1 and 1 and 1, but charge is not conserved. Marcy, explain why charge is not conserved.
There's 2 on the left and 1 on the
Right, we have a +2 on the left and a +1 on the right, so I'm just going to use the marker here. This is +2, this is +1. This is 0, this is 0. I'm using a magnet just trying to help you give you a visual. Trying something different this year. I usually just kind of go over it real fast. All right, Marcy, so if we have +2 on the left and +1 on the right, that's not conserved. We need the same charge on both sides. What can we do? Yep, very good. But let me back up. If we want to balance an equation, what do we use? What are those? Yes, very good. Coefficients. So we put big numbers in front. So I'm going to stay with you on this one. So where do I need to put a coefficient so we have the same number of charges on both sides? Good. So what do I put here? 2. A 2. Very good. So if I add another potassium with a +1 charge, is the charge conserved now? Yes. +2 on the left and +2 on the right. But Kira, what's the problem now?
No, it's not balanced.
The mass isn't conserved. Right. So we do have the same number of charges, but now we have too many atoms on the right, not enough atoms on the left. So what do?
You need to put a 2 in first K.
We add another K, so now we have conserved mass and charge. So what everybody wants to do, you know what? I'm not going to say it. Never mind. I'm going to leave it alone. Maybe you got it. I'm not going to say what kids always do wrong until you do it, and then we'll fix it. No. Maybe that's what I do every year. I always say, this is what they do wrong, and then I show them, and then everybody does it. So I won't show you this year. We'll see what happens on the homework. So anyways, that's how we do it. That's how we do it. We need a 2 in front of the K to give +2. Then we need a 2 in front of this K because now you have 2 atoms and 2 atoms. So be careful. When you put coefficients in redox reactions, you can change the charge with the coefficient. So be careful with that. Okay? Not just the mass, but you're also increasing charge depending on where you put the numbers. Questions on this? All right. So that's the easy part, and that's what the homework wants you to do on the second sheet. You're going to balance what I just did there. Essentially, you're just balancing. Okay, you're using coefficients to balance this, but you have to make sure charge is balanced too. That's the tricky part. Okay, next part of that homework. It says identify who's oxidized, who's reduced. All right. Earl, what's the acronym for oxidize and reduce? The line.
GERD.
That's one of them. GERD.
Leo
GERD. Lose electrons, oxidize. Lose electrons, oxidize. Gain electrons, reduce. Gain electrons, reduce. All right. So I'm going to show you the 2 half reactions. So here's our half reactions. We have oxidation and we have reduction. These are called half reactions because half of this reaction is undergoing oxidation, half of it is undergoing reduction. Together that makes a whole reaction. All right. So here's where you guys, I hope, can figure it out. If you look at potassium, it's going from a 0 to a +1. Iron is going from a +2 to a 0. So, which species, and that's how the regents will word it, which species, the K solid or Fe +2, We don't care about products because they are the result. Now, listen carefully now. Products are the result of oxidation and reduction. So when a Regents question says which of the following species is oxidized or which of the following species is reduced, we don't care about products. They're what happens after the reduction and oxidation. So we're talking about reactants. So which one of these two is oxidized, which one is reduced? And earlier when Mackenzie said it's reduction because the charge goes down, that really helps answer this question. So if you can look and see which one of these the charge decreases, that's the one that got reduced. It gained electrons. And then the other one is oxidized. It's always one or the other. There's only two choices. So if you figure out one of them, the other one is the answer by default. So, I'm done talking. Who can tell me? K solid, Fe plus 2. Who's oxidized? Who's reduced? I feel good that a lot of you know this, so someone's got to volunteer up the answer. Who's it going to be? No one wants to answer. Morgan?
Fe is reduced
How do you know?
because it's going from 2 to 0.
Right, so the charge is decreasing or reducing. So Fe plus 2 is reduced. So Fe plus 2 is gaining electrons. K0, by default, is oxidized. It's losing electrons. Slade, how many electrons are being transferred here?
1.
Now, when I say transferred, I mean the species who is losing the electrons is giving those electrons to the species that's being reduced. They're playing catch with electrons. Okay, you can't play catch by yourself, not really. Okay, so the K is throwing the electrons, Fe plus 2 is catching them. So how many? 1, 2, 3?
2.
Why 2?
Because it's Fe plus 2.
Because it's Fe plus 2. But K only forms a plus 1.
But there's 2.
Ah, there's 2 of them. Tricky. Good job, Slade. Here's how we write our half reactions. He's right. 2 electrons are being transferred. 2K solid with a 0. Copy down everything you see exactly. 2K0 yields 2K plus 1 AQ. I can't stress enough that we copy it down exactly as it is. Plus, now the plus is the number of electrons that K lost. Each K lost 1 electron. And since there's 2 of them, it's 2E minus. How do you know it's 2E minuses besides what I just said? 0 to plus 1, there's 2 of them, so that's 2 electrons. Conservation of charge. If this side of the arrow adds up to 0, and this side of the arrow is plus 2, the only way to balance that out is to add 2 electrons to this side. So 2 negatives, 2 positives equals 0, that equals 0. So charge is conserved or balanced. Now, the rule with redox, just like if you were going to go play catch with somebody, if K throws 2 electrons at iron, iron catches 2. So imagine you're going, I don't know, go outside throwing the football around. Okay? I'm playing catch with Mariana. I throw the football. When I throw 1 football through the air, it doesn't split into 10 footballs, and she just, gets pelted with footballs. If I throw 1, she catches 1. That's how catch works. Chemistry is the same way. If 1 atom throws 1 electron, the other one catches 1. If 1 throws 3 electrons, the other one catches 3. Why am I stressing this? Because if K is losing 2, then you know iron is gaining 2. There's never a difference there. It's always the same number of electrons transferred. So, redox half reaction, reduction half reaction, we write Fe plus 2 because that's who's being reduced. And we have to show gaining 2 electrons. And then an arrow. So Fe plus 2 gains 2 electrons, and as a result, turns into Fe0 solid. So that is how you do a redox reaction. You balance it, you figure out who's oxidized, who's reduced, you write your two half reactions. The most important part of the two half reactions is right here. How many electrons are released, how many electrons are gained, lost or gained, right, Leo Ger, and that's it. There's nothing I could teach you anything different than that example. That's everything you need to know for a redox reaction, how to balance it and how to write the two half reactions. So your homework, this page right here, you don't have to write out all the half reactions. However, you do have to tell me which one is oxidized, which is reduced. So you're going to have two reactants. Tell me which one is which. And then you have to tell me how many electrons are transferred. So you're basically doing all of this anyway. You just don't actually have to write these two half reactions. Okay, so the next work, so you got these two worksheets. The next week, I guess, or Thursday going into the next week, I'm going to give you one where you have to do more of this. All right, so I'm going to say that we can try and do 5B and C. Right, so you're doing 1, 2, 3, 4. Skip 5A because it's really squirrely. So try and do 5B and 5C. And 5B and 5C are this. You see where it says oxidation reduction? You're doing your half reactions. So make sure you balance it first and then do your half reactions. I'm going to try and squeeze in another example. I'm going to go quick so you have two examples in your notes to help you do this. Okay? I think some students sit down and do their homework, they don't look at their notes. I don't understand. If you get confused, please look at your notes. It's supposed to help you do your homework. So let me do one more. Not really pausing for questions, I know, but I'm going to try and get one more example here of all this business. Okay. So I'm going to give you one that's more similar to the numbers 5B and 5C. I'll give you one similar to that. So let's go with, we'll go with calcium, Ca solid, plus aluminum bromide, AlBl3, AQ, yields CaBr2, AQ, plus Al, solid. So this one's a little harder. I left the spectator ion in there, that's the Br. Br doesn't do anything at all in this reaction. I'll explain why in a minute here. So go ahead and copy that down. So on this sheet here, again, I'm trying to help you do the homework. So on 5B and 5C, what the first thing you're going to do is, besides balance the second thing, sorry. The first thing you're going to do is label all the oxidation numbers. That's the first step. First step. So all redox reactions, we're labeling charges. And I'll explain again how we know this is redox in a minute. So calcium solid, 0. Any elements or compounds, solid, liquid, gas, give them a 0. Al solid, 0. Elements by themselves, pure state, solid, liquid, gas, whatever they always are neutral, so give them a 0. Now, we know AlBr3 is neutral overall as a compound, but individually it's ionic, so they're using their charges. I'll just help you out here. Al is plus 3, Br is minus 1. If you can't label charges, then you're in trouble. Ca over here is plus 2, Br is minus 1. So again, Br is a spectator, and how do we know that? It doesn't change. It's a minus 1 on the reactant side, it's a minus 1 on the product side, so nobody cares about Br. You can almost cross it right off. Okay, we could just do this essentially, because nobody cares about the Br. It doesn't do anything in the reaction. The only two elements that do anything are calcium and aluminum. And this is how you know it's a redox. Redox always shows elements changing charge. So calcium goes from 0 to plus 2, aluminum goes from plus 3 to 0. That indicates electrons are being lost and gained. If you see charges that are changing, that's redox, transfer of electrons. I feel like I'm going over a lot here. Hopefully you guys are staying with me. So now the next step is to balance this. So again, I'm going to just kind of do this quickly here. So we have 1 Ca, 1 Ca, 1 Al, 1 Al. It is balanced except we do have the Br. So even though they're spectator, we have to balance them because our charge is not balanced. Our charge is not balanced. We have plus 3 on the left, we have plus 2 on the right. what's the next number they have in common? I don't know the math term, but you know what that is. So the next number 2 and 3 have in common? 6. So we have to put a 2 here, that's positive 6, and a 3 here, that's positive 6. So now our charge is conserved. Our charge is balanced. What's not balanced is the mass. We have 1 Ca, we have 3 Ca. That doesn't work, so I need a 3 here. I have 2 Al, I have 1 Al. That doesn't work, so I need a 2 there. So again, balancing charge and mass are kind of separate. I would balance charge first, then do the mass afterward. That's how I do it. All right, so now we have to say, is it calcium or is it aluminum? Which one is oxidized and which one is reduced? So calcium is going from 0 to +2. Aluminum is going from +3 to 0. So again, I really kind of focus on that word reduction. Leo Ger, lose electrons, oxidize, gain electrons, reduce. So, I guess Slade, I don't know, I feel like I moved around enough here today, around different people. Slade, is it Ca or Al that's reducing in charge as it forms a product? Al. Al is reducing. It's going from +3 to 0. So this is our reduced or reduction. Al +3 is reduced. That means Ca is oxidized. Again, that's our Leo, that's our Ger. Right? Leo means lose electrons, oxidize. Ger, gain electrons, reduce. All right, so now we write our 2 half reactions. This 3Ca0 is oxidized. This 2Al +3 is reduced. Yields 3Ca +2. And we have to figure out how many electrons 3Ca is losing. Anybody want to take a stab at that? How many electrons is it losing? Total. Each Ca goes from 0 to +2, but you have 3 of them. So 6. 6 E minus. If calcium's losing 6, aluminum is gaining 6. They're playing catch. Aluminum gains 6, and as a result, turns into 2Al0. That is a pretty standard to slightly difficult redox question. Okay, the first one we did would be a more standard to easy question. This one's a little bit harder. All right, so you got your worksheets. You guys who just came in, come on up. Let me talk to you quick.